Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving an interesting exponential equation. We have 2i to the power z equals 1 plus I, and we're going to be solving for z values. And at the end I'm going to show you something that will kind of help you solve this problem in a different way. You probably recognize this. If you're familiar with complex numbers, you probably know, I'm hoping, the relationship between 2i and 1 plus I. But if you're new to complex numbers, go ahead and check out my lecture videos. If you like algebra, number theory, and trigonometry problems, go ahead and check out Cyber Math, which is another channel of mine, which is my very first channel. By the way, that's cyber with an S, not with a C. Great, so we have this exponential expression, and obviously our goal is to solve for z. Can you just log both sides like ln 2i to the z equals ln 1 plus I? And then just bring the z over here. From properties of logarithms, you get z times ln 2i equals ln 1 plus I, and then divide both sides by ln 2i, whatever that means. You get ln 1 plus I divided by ln 2i, and that should be the answer, right? Yes and no. Well, it could be one of the answers, but what does that mean, right? What does ln 1 plus I mean? Can you simplify this? And of course, this is multi-valued. When you log a complex number, it's called the complex logarithm. And there's a way to write it, but there are multiple branches. There's infinitely many ways to represent it. And depending on which branch you choose, you get different answers, okay? So how do we approach it then without just logging both sides, right? So we're going to go ahead and use the polar form. Thanks to Euler, any complex number can be written in polar form. And what does that mean? Let me explain. So if you have a complex number, let's say in the complex plane, which we call the argon plane, by the way, this is the imaginary axis, this is the real axis. And if you have like a complex number, let's say a plus bi, which is the name of this channel, right? Hopefully you won't forget. We can basically, let's call that number z, a plus bi, and suppose, for the sake of simplicity, that a and b are both positive. And it doesn't matter if they're negative or something else, but let's just go ahead and represent a complex number with a dot. You can also connect it to the origin and also express it as a vector, no big difference. But connecting it to the origin actually brings us another concept, which is the angle that it makes with the real axis in the positive direction. And you got to remember that positive direction is counterclockwise, CCW, which is this direction. Make sense? Okay. Now, what does that mean though, right? Well, this basically gives you a way to express it using trigonometry or even exponentials. So the distance of z from the origin, 0, we're going to call that the absolute value of z, which you can also denote by using r. R is also called the modulus of the complex number, and theta is called the angle or the argument. You can also abbreviate it with the ARG. For modulus, I don't think there's a shorter form, but here's what this turns out to be. Z can be written as r times e to the power I theta. Of course, r can be replaced with absolute value of z. That's what it is. And to find the absolute value of z, which is r, you can just write it as the square root of a squared plus b squared. This is from the Pythagorean theorem. Okay, so I'm kind of giving you a quick overview of the polar form. You can also find this information in lecture videos. Go ahead and check them out. Now, how does this help us? Well, first of all, we have a complex number in the form of a plus bi. This allows us to turn it into an exponential form, which is beautiful. And Euler said that, which he discovered, which is amazing. E to the I theta can be written as r cosine theta plus I sine theta, which is beautiful. This gives us the most beautiful equation in math. Why? Because you have an exponential with imaginary numbers, and then all of a sudden it just turns into something trigonometric like this, which is unbelievable, right? Don't you think it's one of the most beautiful things? Or maybe the most beautiful thing in math. But anyways, So how do we use this information, right? So you need to find two things, r and theta. And let me explain how this works. You can take a plus bi and then factor out the r like this. And then inside you're going to have a over this so that distributive property works properly. And then inside you're going to have something like this, right? Okay, so when you distribute, you're going to get the original a plus bi. But what this tells you is that if you compare it to this, you have to find out basically an angle whose cosine is this and whose sine is this at the same time. Because sometimes sine and cosine can be both positive or both negative, but it'll occur in different quadrants. So you have to make sure both of these are satisfied. And how do you do that? Is actually there's one way to look at it. You can divide this by that, which gives you tangent theta. So tangent theta, and you can also see that from here, b over a, right? It's always b over a. If tangent is negative, you're in the second quadrant or the fourth quadrant. Does that make sense? The quadrant is important. That tells you what your angle is going to be. And there's obviously many ways to write it because theta, you can add multiples of 2 pi to it. So we need to talk about something called principal argument. But anyways, let's start with 2i. So if you think about plotting 2i is going to look like this. You're going to be 2 units away from 0, and the argument is going to be pi over 2, right? This is 2 units. Why? Or you can write it 2i units because that's on the imaginary axis, 2 units away from 0. This is the real one, and it has no real part because it's imaginary, right? And what about the 1 plus I? 1 plus I is going to be very different. It's just going to be like here, and it's going to make an angle of pi over 4. So we can basically express each one of these using these arguments. And the modulus for 1 plus I is going to be square root of 2 from the Pythagorean theorem. Now we are ready to cook, okay? Let's go ahead and set up our equation. 2i to the z is 1 plus I. We're going to replace 2i with 2 times e to the power I times pi over 2. But again, we are allowed to add multiples of 2 pi, so let's just go ahead and add 2 pi n, where n is an integer, and then we're going to go ahead and raise it to the power z. By the way, these 2 and z look alike, but this is 2, that's a z. So I put a little line through it, you can tell. And 1 plus I is going to be written as root 2 times e to the power I times pi over 4 plus 2 pi k. Now, some people say we don't really need both of these like n and k, and Wolfram Alpha can probably tell you which one is more proper. But anyways, at this point, it would make sense to use the natural logs, right? If you natural log both sides, you're going to get z times ln this, 2 times e to the power I pi over 2 plus 2 pi k. And then on the right-hand side, you're going to have ln of a product, which is root 2 times, did I get that right? Yep. And then obviously the next thing I'm going to do is going to be the taking the natural log of the product, right? Okay. And this is going to be brackets. Now let's go ahead and bring it, let's move this to the left so you can see better. Oops, I left something in there. All right, anyways, I'll take care of it. I think this is going to be the pi over 4, right? And this was I times that. Okay, here we go. Now, what's going to happen here? Oops, I also left some stuff there when I moved stuff. Okay, so here's what it looks like. And when you ln a product, it's going to look like what? ln AB is ln A plus ln B. So this is going to be like z times ln 2 plus I times pi over 2 plus 2 pi k. And then on the right-hand side, you're going to have ln root 2 plus I times pi over 4 plus 2 pi k. By the way, on the left-hand side, I think we have an n, and here we have a k. So this should be a 2 pi n, and this should be a 2 pi k, okay? So this will be an n, again, 2 pi n, and the other one is a k, okay? So far, so good. Now we can go ahead and use division here to isolate z. Z is going to be ln root 2. And by the way, I can write it as 1/2 of ln 2 plus I times pi over 4 plus 2 pi k. K and n are integers, by the way, divided by ln 2 plus I times pi over 2 plus 2 pi n. Now, something interesting happens here. This is the general solution, right? But do we really need k and n? Both. Let us know in the comment section what you think, and we'll discuss. But then when n and k are both 0. Something interesting happens. Let me show you. These will disappear. We're going to have a simpler solution. 1/2 ln 2 plus I times pi over 4 divided by 2. Oops, not 2. I meant ln 2 plus I times pi over 2. And if you don't know what it is, let me show you. We can basically factor out a 1/2 here. And then inside you're going to have ln 2 plus, now think about it. What would you multiply 1/2 by to get pi over 4? Of course, the answer would be pi over 2. And in the denominator, guess what we have? The same thing, right? And what that means, since this is not 0, we can go ahead and get rid of that actually. So these two cancel out, leaving us with 1/2. Wow, that's pretty interesting, isn't it? And why is that happening? Let me tell you. Z equals 1/2 is a particular solution, but of course, like I said earlier, there are infinitely many solutions. This is just one of them. And here's the general solution. I don't think I wanted to frame the other one. So let's go ahead and delete that. So this would be a particular solution, but this solution is actually more general. But let me show you. If you know this fact, this is going to help you. If you take 1 plus I and square it, you're going to get 1 plus I squared plus 2I. Oops, I forgot to tell you. I squared is equal to -1 because I is the square root of -1. And I squared and 1 cancel out, leaving us with 2I. Uh-oh, what are we talking about? We're basically taking this number. So in other words, if you raise both sides to the power 1/2, you're going to get another interesting equation, which is actually what we were looking for, right? Because the problem was asking for 2I to the power what number equals 1 plus I. Of course, z equals 1/2 is not the only solution. It's just one of the solutions, probably the most obvious one. But of course, if you're looking for a general solution, then you must write the answer this way. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe. Take care. Don't forget to check out Cyber Math and A+BI, and bye-bye.